Out past the bright, familiar sky, the radio universe keeps time in rhythms we can't see. Most signals flare once and vanish. Some repeat fast, milliseconds, seconds, like cosmic lighthouses. But this one is different. Imagine a source that turns on, sends a burst of radio energy for up to a few minutes, then goes quiet, and returns again on a cycle of about 21 minutes, over and over. Not for a night. Not for a season. For decades. That's not a rumor. It's an observational result. Astronomers identified a long-period radio transient now labeled GPM J1839-10. Its pulses can vary dramatically in brightness, and each burst can last from tens of seconds to several minutes. When researchers traced the pattern back through radio archives, the same repeating behavior showed up as far back as 1988, meaning this is not a one-off anomaly or a modern instrument glitch. It's a persistent astrophysical source that has been ticking in our data for a generation. And here's the hook. Objects that emit coherent radio pulses are usually explained by rotating, strongly magnetized compact stars, but maintaining that kind of emission at such a slow rhythm is hard to reconcile with standard models. So the story isn't, we found a weird blip. The story is, the sky has been quietly broadcasting a 21-minute heartbeat for decades, right under our noses, and we still don't fully know what it is. Let's strip this down to what the data really says. No speculation, no mythology. The source is cataloged as GPM J1839-10. What makes it extraordinary isn't just that it emits radio pulses, it's the time scale and behavior of those pulses. When it's on, the emission appears as bright radio bursts that can last from tens of seconds up to several minutes. Then it drops back into silence, and the cycle repeats with a remarkably stable rhythm of about 21 minutes between bursts. This is not a single detection from one telescope on one night. The repeating behavior was confirmed across modern observations and then traced in archival radio data, where the same pattern is present at least back to 1988. That long baseline matters. It tells us we're not dealing with a transient artifact, a short-lived outburst, or a one-time instrumental mistake. We're looking at a source that can remain active on this unusual cadence for decades. Another key observational point, the bursts are not identical. Their brightness varies, and the emission can show structure within each active window. In other words, it's not a metronome-perfect beep. It's more like a repeating beacon that flickers, still locked to a long-period clock, but with real astrophysical variability inside each cycle. So, in factual terms, the phenomenon is a persistent radio source, producing minute-long bursts, repeating on 8's 21-minute cycle, observed in modern data and confirmed in archives back to 1988, with variable intensity and burst morphology. That combination is exactly why it forced astronomers to rethink what kinds of compact objects can power coherent radio emission on such long periods. For more than half a century, astronomers have used a simple idea to interpret repeating radio signals. A compact object spins, and we see a beam sweep past us like a lighthouse. That framework works extremely well for pulsars, rapidly rotating neutron stars, because most of them rotate fast enough to keep their magnetospheres electrically active. In the standard pulsar population, rotation periods are typically tens of milliseconds to a few seconds. That's the regime where the physics of charged particles and strong magnetic fields can continuously produce coherent radio emission. Now compare that to GPM J1839-10. Its bursts don't repeat every second. They repeat roughly every 22 minutes. That timescale is not a small outlier, it is a fundamentally different part of the period map. If you take the classic lighthouse picture literally, a 22-minute rotation would mean an object spinning so slowly that, in many conventional models, it should struggle to generate the voltages and particle acceleration needed to power pulsar-like radio beams at all. In other words, the signal isn't strange because it repeats. It's strange because it repeats on a timescale where our usual pulsar machinery is expected to weaken dramatically. That mismatch is exactly why astronomers treat this as a serious clue, not just a curiosity. A periodic radio source in the minutes to hours range pushes on the edge of what we think compact objects can do, And it forces new questions. Are we seeing an extreme neutron star in an unusual state? A different kind of compact object? Or a mechanism that looks pulsar-like in the data but is physically different under the hood? This is where the label matters. Objects like this are now discussed as long-period radio transients, a recently recognized, actively researched category of sources that emit radio pulses with periods far longer than ordinary pulsars, sometimes with pulses lasting tens to hundreds of seconds while the gaps between them stretch into minutes or more. The key point is simple and fully factual. The timescale itself is the mystery. It doesn't fit comfortably inside the standard pulsar box, and that's why the discovery is important. And that's the pivot for the story. Not aliens, not magic, just a signal that sits in the wrong place on the timeline, daring our best models to explain how it can stay on for decades. For decades, this part of the sky looked quiet, until modern instruments started listening in the right way, with the right cadence, and with the right sensitivity. What we now call GPM J1839-10 didn't announce itself with a single dramatic flash. It revealed a pattern, radio bursts that recur about every 22 minutes. That's a timescale that's easy to miss if you're only scanning for millisecond pulses, or if your observing strategy isn't built to catch something that waits that long between events. A key moment came with Meerkat, a 64-dish radio interferometer in South Africa designed to map faint radio structures with extraordinary clarity. In July 2022, Meerkat detected a sequence of these bursts from the same sky position, repeating with that unusually long cadence. This wasn't a one-off glitch. It was a signature, regular enough to track, strange enough to challenge assumptions about what kinds of objects can produce coherent radio emission on minute-long cycles. And once researchers knew what they were looking for, the story became even more unsettling, in a good, scientific way. They went back into archival observations. Not to force a match, but to test a straightforward question. If this source is real and persistent, could it have been hiding in existing datasets all along? The answer was yes. Archival detections show this behavior stretching back decades, meaning the phenomenon is not new, it's newly recognized. This is where viral timelines often fall apart. A common claim online is, astronomers found it in 2002 using the MWA radio telescope. The problem is simple and factual. The Murchison Wide Field Array, MWA, began operations years later. So, MWA in 2002 cannot be correct as a literal statement. That doesn't mean nothing happened in 2002. It means people are often mixing together a real long-term archival footprint, different instruments and surveys, and a dramatic date that sounds authoritative on a short-form platform. In real astronomy, discovery stories are rarely a single timestamp. They're chains of evidence, a strong modern detection, followed by careful cross-checks against older data, followed by a statistical and physical analysis that asks, is this repeatable? Is it astrophysical? Is it consistent across independent instruments? That's what makes this case valuable. Not because it's mysterious in the supernatural sense, but because it's a genuine observational outlier that forces the field to widen its models. Objects that behave like radio beacons, but on timescales that don't fit neatly into the classic pulsar picture. This isn't aliens versus nothing. It's something better. A real signal, real timestamps, real telescopes, and an open scientific question about the engine underneath. First, the clean, verified placement. This source is associated with the Scutum constellation, projected along the dense band of the Milky Way. That matters because the galactic plane is crowded, full of ionized gas, overlapping radio sources, and foreground effects that can blur or distort what we think we're seeing. In other words, even when something is real, it can be hard to recognize what it is. Second, the distance. Published reporting describes it as being inside our galaxy, with an estimated distance around 15,000 light-years. That number is not a tape measure result. It's a best estimate based on how the signal interacts with material between the source and Earth. So the honest way to say it in a NASA-style script is about 15,000 light-years, and treat it as a scale marker, not a precise pin. Now the part that makes it cinematic without inventing anything. If it's roughly 15,000 light-years away, then every burst we detect today began its journey about 15,000 years ago. The object didn't suddenly become mysterious in 2022 or 2023. What changed is our ability to notice. Modern wide-field surveys, long baseline monitoring, and software designed to detect patterns that don't match the old categories. So this segment lands a simple, factual punchline. A repeating radio beacon in scutum, inside the Milky Way, far enough that we're listening to ancient emissions, close enough that it's part of our own galaxy's population of extreme stellar remnants. For something this strange, the most important clue is not the brightness, or even the 22-minute rhythm. It's the time span. When researchers searched radio archives, they found the same source repeating since at least 1988. Not a one-night anomaly. Not a seasonal artifact. A signal that shows up across decades, with a cycle that stays remarkably consistent. That kind of persistence immediately changes the scientific conversation, because a lot of dramatic explanations are, by their nature, short-lived. One-time explosions, brief interactions, events that should fade, drift, or simply not stay on schedule for decades. A source that keeps returning forces a different baseline assumption. Whatever is producing the radio emission can keep operating for a very long time, and it can do so without the system tearing itself apart. Now, this does not mean scientists already know what it is. It means the data narrow the field. Here's what the long timeline lets researchers do that a single detection never could. First, it lets them test whether the clock is truly stable. In the Nature paper, the team uses the archival span to put a strict limit on how fast the period can be changing. In plain terms, if the object is slowing down, it's doing so extremely slowly, so slowly that it strains many standard models for how coherent radio emission is powered and maintained over long times. Second, it reframes the bursts themselves. The pulses are not uniform. Their brightness can swing by about 2 orders of magnitude, and individual bursts can last tens of seconds to several minutes. But the long-term repetition tells you the engine behind them is not random chaos. It's more like a system with a stable metronome, where the volume knob sometimes jumps, but the beat keeps coming back. Third, it sets a hard standard for any hypothesis. It must explain both the slow rhythm and the durability. If a model can't plausibly keep producing radio bursts for decades, it doesn't survive contact with the archive. So what's the honest scientific takeaway at this stage? It's not mystery solved. It's stronger and more precise than that. This is a long-period radio transient that has stayed active for decades, and that fact alone rules out many short-lived scenarios and demands a stable, repeatable physical mechanism. That's why the object matters. Not because it's spooky, because it's a clean, stubborn data point that forces physics to either stretch or to find a better explanation. And that's the real thrill here. The archives don't just preserve history. Sometimes, they reveal an engine that's been running quietly in the dark for most of a human lifetime. What can be said honestly, on the record, is this. The peer-reviewed literature treats GPM J1839-10 as a compact object problem first. The observed behavior, coherent radio pulses, strong polarization, and a stable cadence near 22 minutes, fits naturally into the question astrophysicists already know how to ask. What kind of magnetized, rotating engine can produce lighthouse-like radio emission? That points directly toward neutron star physics, not because it is proven, but because neutron stars are the universe's most reliable machines for coherent radio beams. A neutron star is a city-sized remnant with extreme gravity and an intense magnetic field. In ordinary pulsars, charged particles are accelerated in the magnetosphere and the star emits a beam. When that beam sweeps across Earth, we detect a pulse. It's an elegant explanation, until you look at the clock. A 22-minute timescale is far outside the comfortable territory of normal radio pulsars. Standard pulsar emission models struggle to keep radio production alive when rotation becomes that slow, because the usual pair production and acceleration conditions can shut down. In other words, the signal looks like a lighthouse, but the lighthouse is turning much too slowly for the classic mechanism to work easily. That tension is why the cautious scientific stance is not, it's a magnetar, but a neutron star interpretation is barely viable under classical assumptions, so the magnetosphere and emission physics may need something extra. The literature explores possibilities in that direction. Highly magnetized compact objects, magnetosphere states that switch on and off, and geometries that could produce long, irregular pulse windows without requiring a clean, fast pulsar-like heartbeat. Importantly, this framing stays honest. It does not claim the engine has been identified. It only states that compact object magnetospheric physics is the leading arena where the problem is being fought. The same cautious approach applies to what we don't see. If the source were behaving like a typical high-energy magnetar outburst, you might expect bright X-ray activity to accompany radio bursts. But the observational record discussed in the literature includes non-detections in X-rays during relevant windows, which constrains simple radio burst equals magnetar X-ray burst analogies. That does not rule out neutron star scenarios, but it forces the story to stay tight. Whatever powers the radio pulses may not be announcing itself loudly in X-rays. Finally, responsible science does one more thing. It keeps alternative compact engines on the table. The literature explicitly notes that highly magnetic white dwarfs naturally rotate on minute-to-hour timescales and could, in principle, host coherent radio emission, yet this is not an easy win either, because such radio lighthouse behavior has not been widely observed in isolated magnetic white dwarfs, and known white dwarf, pulsar-like, systems have their own caveats. The point is not to replace one certainty with another. The point is to show viewers what careful looks like. The signal is real, the class is emerging, and the engine is still under active debate. Tone to land. We are not witnessing a solved mystery. We are watching astronomy do what it does best: pin a strange, repeatable phenomenon to the sky, measure it ruthlessly, and then let the universe force new physics, or new astrophysical scenarios, onto the table. When a signal repeats with clockwork regularity, the first instinct is to blame rotation. A compact object spins, a beam sweeps past Earth, and we detect a tick. That picture works beautifully for many pulsars, but long-period radio transients force astronomers to widen the menu of explanations. First, periodic does not have to mean spin. The repeating pattern could be driven by geometry, how the emitting region is oriented and how that orientation changes over time, rather than by a simple lighthouse beam. A slow wobble or precession could tip an emission cone in and out of our line of sight, turning an underlying continuous process into something that looks like distinct, repeating detections. Second, the clock could be external, an orbit. In a system with a companion, the repeating cycle can come from interaction, not rotation. A companion can modulate what we see by feeding plasma into the environment, reshaping magnetic field structures, or periodically blocking, bending, or altering the path of radio waves through surrounding material. In other words, the 22 minutes could be the rhythm of a system, not the spin of a single object. Third, the source's own environment might act like a gate. Even if the central engine is steady, coherent radio emission is sensitive to magnetospheric conditions, particle supply, plasma density, and the stability of the acceleration regions that produce radio bursts. If those conditions switch between open and closed states, you can get repeating windows where emission becomes detectable, followed by quiet intervals. The honest bottom line is this: for GPM J1839-10, these are not competing answers yet. These are competing scientifically plausible mechanisms that can produce long, minute-scale repetition in radio. Rotation is one candidate. Orbital modulation is another. Magnetospheric gating and changing plasma conditions are another. The job now is observational. Measure how the bursts behave across frequency, polarization, and time, and eliminate mechanisms that can't reproduce those signatures. When a signal looks too strange to be real, astronomy doesn't jump to conclusions. It tightens the rules. Step 1 is always the same: prove it isn't us. Radio telescopes live under a constant storm of human-made interference. Satellites, aircraft, electronics, even distant transmitters bouncing through the ionosphere. So teams test whether the bursts behave like a true astrophysical signal. They check whether the pulse properties are consistent with propagation through space, whether the burst timing aligns with the telescope's pointing, and whether the signal persists across different observing setups. If a mystery vanishes when the instrument changes, it was never the sky. Step 2 is stronger. See it again. A single detection can be a glitch. Repeated detections, especially with a different facility, turn a curiosity into a physical object. For this source, modern observations include detections with Meerkat in 2022, which matters because it's an independent instrument with different hardware, different pipelines, and different local interference environments. When the same repeating behavior shows up there, it's no longer just one telescope story. Step 3 is the most powerful. Go backward in time. Astronomy has something rare in science: decades of archived raw sky data. Once a source is suspected, researchers can search old survey recordings from past projects. That's where the story becomes almost unreal. The repeating behavior isn't just recent. It appears in archival observations back to at least 1988. That single fact is a verification engine. A fake, a transient local artifact, or a short-lived instrumental effect doesn't keep resurfacing across eras of receivers, storage formats, and analysis methods. And then comes the final filter: independent scrutiny. Results are written up with methods, uncertainties, and alternative explanations, and they get challenged through peer review and follow-up work. The goal isn't to win a theory. The goal is to reduce the claim to what the data truly forces you to accept. There is a real celestial source. It produces long radio bursts. It repeats on a 22-minute timescale, and it has been active for decades. Everything beyond that, what the source is and how it does this, stays in the working hypotheses box until the evidence gets sharp enough to cut. Here's the clean truth. We do not yet have a single, confirmed physical mechanism that explains everything about GPM J1839-10. We know what it does: long radio bursts, repeating on each 22-minute cycle, seen in modern observations and in archives spanning decades. But turning what into why is the hard part. Right now, researchers are still working through several open questions. First, what kind of object is it exactly? A compact object is strongly suspected, but the data has not locked the source into one definitive identity. Different models can reproduce parts of the behavior, but not with one universally accepted explanation. Second, what sets the 22-minute clock? If it's rotation, that's unusually slow for familiar radio pulsars. If it's geometry or an interaction with its environment, then the timing must stay stable for a long time. Something nature can do, but not cheaply. The clock exists. The engine behind the clock is still under debate. Third, why are the bursts long and variable in duration? Some events can last tens of seconds, others push to minutes. That variability is one of the key constraints any successful theory must match, without hand-waving. Fourth, how does the radio emission actually switch on and off so sharply? In many astrophysical systems, turning on is gradual. Here, the behavior can look like a beacon, appearing, fading, returning, suggesting a powerful, structured emission process, but the details are not settled. And that uncertainty is not a weakness. It's the point of discovery. A new class of object doesn't arrive with a label attached. It arrives with measurements, patterns, and the discipline to say, this is real, this is repeatable, and this is what we still cannot claim. What we're hearing isn't a prophecy, and it isn't space trying to warn us. It's a real, repeating radio transient, bursts that arrive on a long, steady rhythm, measured in minutes, not milliseconds, and visible across decades of data. That alone makes it scientifically valuable. Nature is running the same experiment again and again, giving us repeated chances to test ideas instead of guessing from a single flash. But here's the honest line we have to hold. The exact physical engine is not yet pinned down. Researchers have explored plausible explanations involving compact objects and extreme magnetized environments, and they've used modern observations plus archival records to narrow what can and can't fit. Yet the core question remains open. What mechanism can produce coherent radio pulses on H22-minute cadence and keep doing it for years, possibly decades, without fading into silence? That's not failure. That's how discovery looks in real time. Measurement first, explanation second, and the explanation must survive independent checks. If you want the next episode, I can break down the clean observational tests. What data would separate a rotation clock from an orbital clock? And what telescopes would need to measure to decide, without speculation?